Have you ever watched an A-18 Super Hornet launch from an aircraft carrier and wondered how physics makes the impossible routine? A 40-ton fighter jet sits motionless on the deck. 3 seconds later, it's airborne at 165 miles per hour. No runway, no rolling takeoff, just engineering that seems to defy every law of motion you learned in school. Welcome to Flight Deck. I'm here to decode the engineering reality behind military aviation operations. Today we're exploring how Navy engineers solved a problem that stumped aviation pioneers for decades, accelerating 80,000 pounds of aircraft from zero to flying speed in less distance than a football field. What you're about to discover will change how you think about the relationship between physics, engineering, and human capability. Because when you understand the forces involved in carrier operations, you'll realize you're witnessing one of the most remarkable achievements in mechanical engineering. The challenge seems mathematically impossible when you break it down. Commercial airliners need 8,000 to 12,000 feet of runway to reach takeoff speed. A Navy carrier has exactly 300 feet of deck space before the aircraft must be flying or face catastrophic consequences. Think about what this means in terms of acceleration. That A-18 Super Hornet at maximum takeoff weight needs to reach approximately 165 miles per hour to generate sufficient lift. The physics equation is unforgiving. 0 to 165 miles per hour in 300 feet requires acceleration forces that would crush most mechanical systems. Let me put this in perspective. A Formula One race car, specifically engineered for maximum acceleration, needs about 1,200 feet to reach 165 miles per hour. The carrier-based fighter must achieve the same velocity in 1/4 that distance while carrying weapons, fuel, and complex avionics that weigh as much as several cars. The fundamental question becomes, how do you generate enough force to make this possible? The answer reveals engineering principles that push the boundaries of what mechanical systems can achieve. To understand why this challenge stumped engineers for decades, we need to examine the physics involved. Newton's second law states that force equals mass times acceleration. When you're dealing with 80,000 pounds of mass, the forces required become extraordinary. Early attempts at launching aircraft from ships were spectacular failures, precisely because engineers underestimated these force requirements. They tried pushing aircraft off platforms, using compressed air systems, even explosive charges. The results demonstrated that brute force without precise control creates destruction, not flight capability. The breakthrough came when Navy engineers realized they needed to think differently about force application. Instead of a single massive push, they developed a system that applies controlled force over the entire launch distance. This isn't just about raw power. It's about the precise management of energy transfer from mechanical systems to aircraft. The solution involves 3 critical components working in perfect synchronization: the catapult system that generates and applies force, aircraft engineering that can withstand extreme acceleration, and human factors that allow pilots to function during forces that would incapacitate most people. The steam catapult system represents controlled mechanical violence operating with surgical precision. Below the flight deck, massive steam accumulators store pressurized steam at temperatures exceeding 500 degrees Fahrenheit and pressures that could power a small factory. When launch is initiated, this steam releases into cylinders, driving pistons connected to the catapult shuttle on deck. The force generated equals accelerating a family car from 0 to 60 miles per hour in less than 1 second. But here's where the engineering becomes truly sophisticated. The system automatically adjusts for different aircraft weights and requirements. A lightweight F/A-18 requires different force application than a heavily loaded E-2 Hawkeye. The catapult system calculates steam pressure, release timing, and force curves for each specific aircraft configuration. Too little force, and the aircraft drops into the ocean. Too much force and structural damage occurs, or the pilot becomes incapacitated. The precision required is extraordinary. Launch parameters must account for aircraft weight, fuel load, weapons configuration, wind conditions over the deck, and dozens of other variables. Every launch represents a physics problem solved in real time with zero tolerance for error. The steam system can deliver this precise force application. But even more remarkable is what's replacing it on newer carriers. The Electromagnetic Aircraft Launch System, or EMALS, represents the next evolution in launch technology. Instead of steam pressure driving pistons, EMALS uses linear induction motors, essentially electromagnetic fields that accelerate a conductive shuttle along a track. The advantages are significant from a physics standpoint. Electromagnetic systems provide infinitely variable force control throughout the launch sequence. Early acceleration can be gentler on aircraft structure and crew, with peak forces applied at optimal points in the launch cycle. This precision was impossible with steam systems. Think about what this means for aircraft design. Future carrier aircraft can potentially use lighter structures because launch forces can be precisely controlled rather than brutally applied. The electromagnetic system can vary its acceleration profile to match each aircraft's structural limitations and crew tolerance. But the most remarkable aspect isn't the catapult system itself. It's how aircraft are engineered to survive forces that would destroy any civilian machine. Carrier-capable aircraft represent engineering for extreme conditions. These aren't modified land-based planes. They're designed from the ground up to withstand forces that exceed normal flight loads by massive margins. The landing gear must absorb not only normal landing forces, but also the violent acceleration of catapult launches. The main gear attaches to a launch bar that connects to the catapult shuttle, transferring acceleration forces directly through the aircraft's primary structure. This connection point experiences forces equivalent to the entire aircraft's weight multiplied by 3.5. Wing structures require reinforcement throughout. The airframe connections, control surfaces, and every structural joint must handle stresses that would snap conventional aircraft components. This is engineering for punishment that most mechanical systems never encounter. Consider what happens to the aircraft's internal systems during launch. Hydraulic systems, flight computers, radar arrays, and weapons management systems all must continue operating normally while experiencing acceleration forces that would shut down most civilian equipment. The fuel system presents unique challenges. Jet fuel weighs approximately 6 pounds per gallon, and a fully loaded Super Hornet carries thousands of gallons. During catapult acceleration, this fuel mass wants to continue moving at its previous velocity while the aircraft accelerates forward. The fuel system must prevent catastrophic weight shifts that could make the aircraft uncontrollable. The human factors involved in carrier operations push the limits of what pilots can endure while maintaining operational effectiveness. During catapult launch, pilots experience approximately 3.5 Gs of acceleration for 3 seconds. That means a 200-pound pilot effectively weighs 700 pounds while managing pre-flight procedures and preparing for immediate tactical operations. This isn't just physical stress, it's cognitive challenge under extreme conditions. Pilots must monitor instruments, communicate with the ship, and prepare for formation flying or combat operations while their body experiences forces that would overwhelm most people. The training process teaches pilots specific techniques for managing launch forces. Proper bracing prevents injury, breathing techniques maintain oxygen flow to the brain, and mental preparation ensures they can transition immediately from violent acceleration to precise flight operations. Recovery from catapult launch requires instant adaptation. Pilots must immediately shift from the extreme acceleration environment to normal flight operations. Formation joining, tactical procedures, or combat engagement all must begin within seconds of leaving the catapult. What makes this truly remarkable is how routine it becomes. Experienced carrier pilots launch hundreds of times, adapting to forces that would incapacitate untrained individuals. The human body's ability to adapt to extreme mechanical environments demonstrates capabilities most people never discover. The precision required for successful carrier launches reveals engineering principles that apply far beyond naval aviation. Every launch represents multiple physics calculations solved simultaneously with perfect accuracy. Launch timing must account for wind conditions over the deck, aircraft configuration, mission requirements, and weather factors. The catapult system calculates optimal steam pressure or electromagnetic force curves for each specific situation. Deck personnel coordinate timing to ensure aircraft launch intervals that prevent dangerous interactions. Air traffic control manages launch sequences that put multiple aircraft airborne within minutes while preventing collisions or dangerous proximity. Each pilot receives specific instructions for post-launch procedures, formation assignments, or tactical deployments. The margin for error approaches zero. Insufficient launch speed results in aircraft entering the water ahead of the ship. Excessive force can cause structural damage or pilot incapacitation. Timing errors create collision hazards or mission failures. Yet this complex choreography happens routinely on carriers operating worldwide. The engineering systems work so reliably that what seems impossible becomes standard military capability. Looking at future developments, electromagnetic launch systems enable possibilities that steam catapults couldn't accommodate. Unmanned aircraft with different structural characteristics, potential spacecraft launch applications, and even civilian transportation systems become feasible when you can precisely control acceleration forces. The physics principles remain constant, but our ability to apply them continues evolving. Future carriers might launch aircraft we haven't yet imagined, using refinements of the same force application concepts that make current operations possible. Advanced materials science contributes to this evolution. Stronger, lighter aircraft structures can withstand launch forces while reducing overall weight. Improved human factors understanding helps pilots adapt to extreme acceleration environments more effectively. The electromagnetic systems also offer maintenance advantages. Steam catapults require complex mechanical components operating under extreme pressure and temperature conditions. Electromagnetic systems have fewer moving parts and more predictable maintenance requirements. Understanding carrier launch physics changes how you view these operations. What appears to be routine military procedure actually represents some of the most challenging mechanical engineering achievements in modern technology. Every catapult launch demonstrates humanity's ability to harness fundamental forces and apply them with precision that seems impossible. The combination of steam or electromagnetic power, structural engineering, and human adaptation creates capabilities that extend American military reach across every ocean. The relationship between force, mass, and acceleration isn't just theoretical physics. It's practical engineering that enables global power projection. These principles allow 40-ton aircraft to operate from mobile platforms, fundamentally changing military capability and strategic options. When you watch carrier operations, you're seeing physics principles pushed to their absolute limits through engineering excellence. The forces involved would destroy most mechanical systems, yet Navy aircraft routinely experience and survive these conditions. The engineering solutions developed for carrier operations influence technologies far beyond military aviation. Roller coaster design, spacecraft systems, and industrial machinery all benefit from force application techniques pioneered for naval aviation. The next time you see footage of carrier launches, you'll understand the remarkable physics and engineering that make the impossible look routine. Those 3 seconds of violent acceleration represent decades of engineering refinement and physics application that creates one of the most impressive capabilities in modern military technology. What impressed you most about carrier launch physics? The raw mechanical forces involved, the precision of the engineering systems, or the human factors that make it all possible? Let me know in the comments below. If you enjoyed this deep dive into military aviation physics, subscribe to Flight Deck for more technical breakdowns of how military systems actually work. Until next time, remember that behind every impressive military capability lies fascinating physics and remarkable engineering that pushes the boundaries of what's possible.